Okay, so we're going to go into second derivatives. And second derivatives will help us determine the velocity and acceleration of something. So we'll say that this equation represents a particle moving some place in space. Okay, so it's easy to tell that this is a cubic function. So it probably has some type of pattern like this if we were to graph it on an xy axis, right? When we find a derivative of something, we're finding its velocity. Okay, so when we find the first derivative, so in this case, its velocity would be s prime t, and a lot of times what they call that is vt. So in other words, the velocity, with time being our variable, is equal to the particle speed. I assume this means their speed, the derivative of the particle speed. Okay, becomes its velocity.
Isn't it the position, I think?
Sorry, is it position?
Yeah.
It probably is position. Our second one is acceleration. And acceleration, they'll denote by same idea, same variable t, which would be equal to the velocity, or the derivative of the velocity versus time, and its position, which we call s, which is a second derivative. Okay. So these are essentially different ways to denote acceleration and velocity and its position. I would have called this BAT. Anyways, so we'll go through this process of finding an equation for velocity and acceleration, and then from there we're going to try to discover when things are speeding up, slowing down, when velocity is positive or negative, going one direction or another. And we'll compare all of these by looking at a graph. So the first step is actually finding derivatives, and luckily these are all really just power rules when we're deriving. So if we're to derive this, we'll call the first one v at t, or s prime t. Okay, so we're going to derive the first function, and that'll end up with 3t squared minus 24t plus 36. Okay, so this is our first derivative of the original function. Our second one, I guess we'll do it in purple, which would be our acceleration, or our velocity prime, or our position as a second derivative. And when we find the second derivative, we'll end up with 6t minus 24. Okay, and if you take a look at the three functions, we essentially have a cubic, quadratic, and a linear function. Okay, that's what the three of these are. And we can tell by the power of the polynomial, the highest power in it. In this case, it's just the power of 1. Okay, so we can do a bunch of factoring to find this out. In the first one, I could common factor LT, then put it through a quadratic formula, and find the points where it crosses. And I can put this one through quadratic formula, again, to find points when it crosses. And then we can find an x-intercept, which is a lot of math we can do, and hopefully you already know how to do it at this point. What I'm going to do instead is I'm going to put it on a graph, and we're going to talk about the different points in time, and then we're going to plug in this to solve for one specifically. Okay, so on our graph, we have our three functions here, and I'm looking at the graph of the first one, and this particle's position is referenced to its starting point, and it's supposed to be its position in time, so our x-axis is in time, and its distance from its starting point. So essentially this particle moves along its starting point, and at a time of 2 seconds it is 32, I'm not sure what it's measured, say it's centimeters from where it started, or millimeters, or kilometers for all we know.
Okay? In meters here.
Is it in meters?
Yeah.
Perfect. Okay. It then heads back towards where it starts, and at the 6-second mark, okay, this is our other x-intercept, it's back where it started. Okay. Then it takes off again in the same direction it originally started, and goes that way forever because it's a cubic function. We have no more turns in it, right? So this gives us an idea of its positioning. It starts at 0, okay, and it's a long straight line. So it might be best to really visualize this sideways, and I can give you something like that. It would kind of make this type of, this would kind of be the idea. So if we had our particle starting here, we'll call this at 0. It takes 2 seconds, okay, and at 2 seconds, it's 32 meters away from it started. Then it decides to turn back. Okay. At 6 seconds, it's back here again. So this was a 4-second interval the second time, so it's moving slower this time. And then finally, in its last move, it goes in this direction forever. Okay, but it's moving along the same straight line, so it goes 32 meters away, back to where it started, and then takes off. That's essentially its position. Next thing we're going to look at is reference to its velocity, okay? And the velocity of this function, okay, is going to be very important. We have our point here. This is our starting point, its velocity, okay? And our x-intercepts, do you know what they're going to represent for our velocity?
When it's not moving?
Yeah, essentially when it's changing its direction, right? It's going to be a point where it stops. And it doesn't technically have to change direction. It could stop and then continue in the same one. But in our case, we already know at 2 seconds it changed direction.
Right.
And then at 6 seconds, it changed direction again. Okay? And essentially what's happening is whenever we're above the x-axis, we know we're moving in positive direction. Okay? So, oops, sorry. That's the same idea of, we'll consider this our positive direction, okay? So this is when we're going in our positive direction, and when we're heading leftward, we'll consider that, just for argument's sake, our negative direction to make sense of it on the graph, okay? So our positive, whenever we're above the x-axis, we were heading to the right, which we called our positive direction. And then at 0, or our x-intercept here, it changes direction, and then it switches directions all the way to 6 seconds. And we know at 6 seconds, it gets back to where it originally started and then takes off again, going in that same positive direction. So everything below here, okay, I can try to show this graphically here. Let's see, V, and we'll give it a little parameter. Let's do this. There we go. That's kind of the idea I was trying to get to. That anything down below here, we know we're heading to the left, and anything above that, we're heading to the right. That's the idea of this function in reference to it. And we can kind of see it in reference to our original one, because we know right here, this is our turning point, right? Essentially, when it's stopped and changed directions, our velocity is 0. We're not going anywhere. We're changing direction. And then again, it crosses at our other changing point in terms of the particle. The particle changes directions at this point. These are considered local max and local min, so kind of get it to that later in the course. And finally, we'll talk about the acceleration, okay? The acceleration of this product, and let's move this guy here. This is our graph for the acceleration of what we're doing. And what we need to do is we need to really compare acceleration to our velocity, okay? We compare our acceleration and our velocity because our acceleration and velocity, when multiplying values together, okay, it really tells us if the particle is speeding up or slowing down in a certain direction, okay? So I'm going to just take a spot here. Let's say we're at roughly the value of 1, okay? We know at 1 I'm at some positive value, right? I'm at some positive value. Try to get as close to 1 as I can. There you go, 1 in 15. That's a great one. Okay? I know my y value is positive, where in this case, 1, my y value is negative. Okay? So when I multiply a negative and a positive together, I'm getting what's considered a negative value. And what that means is we're decelerating. So I'll try to write this out in function notation. But the idea to this, extend this page, is, and I think they have a rule written down somewhere in your book here, similar to this. Let's see if they have it. Yeah, it's essentially this idea here. An object is speeding up, so we'll say speed is up, when we can take our velocity and we can multiply it by our acceleration, and it's greater than 0. Essentially, when you have a positive, we're multiplying the two together. And we're slowing down, or I'm just going to call it speed is decreasing, okay, when velocity times the acceleration, okay, is less than 0. And we'll call that, essentially, less than 0 is a negative value, okay? So when we go and look at our graph here, we're looking at, and in this case, 4 seconds is important. This is when our velocity and our acceleration are, looks like a 0 point here. If we were to multiply these together, this is a 0, times a negative, we have a 0 here. So this is our point where we're neither speeding up or slowing down. Okay, so anything where we multiply our values, so for instance, in this little region here, from here, all of our velocity is negative, right? And all of our acceleration is also negative, right? So everything in that range is a negative and a negative. And we multiply those two, what do we get?
A positive.
A positive. So when we multiply those two negatives, we're getting something that's speeding up. Okay, so essentially this particle's speed is not constant at all time. It's probably, and we can, I shouldn't say probably, we can actually solve for it, but let's just give it an idea. It might be doing something like it speeds up, then starts to slowly get to here, turns around, speeds up, slowly gets to here, turns around, and maybe takes off at an increasing acceleration all the time. Okay, that's a logical idea. And especially because we know that these are positive and our acceleration is positive. Because those numbers are getting larger and larger, our speeding up or the speed of the particle is increasing more and more and more. So we want to always reference these two graphs. Now you can take any point in time, like we did there with 4 seconds, but I could take any point in time and maybe look at what would be a good value. 6 is 0. I don't want to use a 0 value. I'm trying to think what would be a nice number. Maybe 3 would be a good number. And we'll go back and algebraically look at the value of the number 3. Okay? Let's look at the number 3 in terms of this. If we were to plug 3 in, it would give us our position in time if we plug 3 in. So let's see if we can quickly do that on a calculator without having to do too much. 3 cubed gives us our 27. And that's going to be 27 subtract 3 squared is 9 times 12 is our 106, I think. Let's see, minus 12 times 9, 108, okay. And that gives us a negative 81 plus, and we'll do bracket 36 times the value of 3 and bracket 27. So at 3 seconds, the particle's position, so we'll call this, we'll do it in green here. At 3 seconds, the particle's position is 27 meters from its starting point. Okay, we know from previous knowledge that it was heading in this direction at 3 seconds. So this is where we are at that point in time. If we plug 3 into our velocity, that's going to give us 3 squared is 9, 27. Minus, let's get a value here, 27 subtract our 24 times 3 and bracket 72 equals, so negative 45 plus 36. Okay, our velocity is actually a negative value at negative 9. Okay, so we'll say v at 3 is negative 9. S at 3 we said was 27, and A at 3 will give us 18 minus 24 is negative 6. Okay, so we have negative 6. Okay, so and actually at 3 seconds, and this makes a lot of sense. So let's take this information. We're 27 meters away. We know that at 2 seconds it turned around, right? So it was actually on its way back at 27 meters away. And we know that because our velocity is negative 9. Our velocity is a negative number, so we knew we're heading in that negative direction, back this way, okay? And our acceleration is a negative value, so it's also accelerating in this way. So we're going to multiply those two together, right? Like we said about this concept down here, velocity times acceleration. We multiply our 9 times our negative 6, and we end up with our 54, but more importantly, positive 54, which means it's speeding up. So in other words, it's actually moving to the left and an increasing speed. It's constantly getting faster and faster. Okay, does that idea kind of make sense with velocity and acceleration? There's tons of info we get from one little equation, right? And comparing all 3 of them graphically can be hard, but if we can try to pick a specific point, we can really tell what's going on at that time.